All right, we're going to do section 5.8 supplement. I'm going to go through the trig substitution to show that the integral that we evaluated by recognizing that it was a inverse hyperbolic trig function form is the same result that we would get by going through and doing the trig substitution, which is something we can always do with these types of integrals. We just save some work if we recognize the form as an inverse hyperbolic trig function. So, in class, the problem that we were doing was we wanted to evaluate this indefinite integral. 2 over x square root of 1 plus 4x squared dx. We recognized that this was an inverse hyperbolic trig function, and we said that it came out to, finally, negative 2 natural log of 1 plus square root of 1 plus 4x squared all over the absolute value of 2x plus c. And this was the inverse hyperbolic cosecant form. We're going to show that we get the same result by trig substitution. So I'm going to draw my triangle. I always draw a triangle for trig substitution. So here's my triangle. We'll call this theta. Here's my right angle. I'll label this side 2x, call this side 1. So this side is 1 plus 4x squared. Square root of 1 plus 4x squared. So cosine theta equals 1 over square root of 1 plus 4x squared. Tangent theta is 2x, or I can write it 2x over 1. Cotangent theta is 1 over 2x. So if I solve this, I get x equals to come up with my dx. X equals 1/2 tangent theta. Dx is 1/2 secant squared theta d theta. And now I think we have everything we need to put into our integral. So we have here when I substitute these values into the integral, we have 2 times the integral of cosine theta over 2 tangent theta times 2 secant squared theta d theta. And I'm just going to rewrite this a little bit. So this is 2 integral. I'm going to write cosine theta over sine theta the 2's cancel, so here's my tangent, 1 over my tangent times cosine theta. I'm going to write this all out. Here's my cosine theta times 1 over cosine squared theta d theta. Just so I can see all my cancellation. And this finally gives me, this equals 2 integral of 1 over sine theta d theta, which is 2 times the integral of cosecant theta d theta, which we remember is negative 2 natural log absolute value cosecant theta plus cotangent theta plus a constant. And I can do my back substitution for cosecant and cotangent, and this finally comes out to -2 natural log square root of, the absolute value of 1 over square root of 1 plus 4x squared over 2x plus 1 over 2x plus c. And you see here that the forms are not exactly the same. We can, if we find a common denominator and add these, then we would end up with the same form. So through trig substitution, we end up with the same form, and this is also the inverse hyperbolic cosecant of 2x times -2, just like we talked about in class. So we end up in the same place, recognizing that it's an inverse hyperbolic trig function form, or going through trig substitution. Saved ourselves some work when we use the inverse hyperbolic trig function method. All right, so let's look at a tractrix. A tractrix is a type of curve called a pursuit curve. At one point in time, it was called the pursuit curve. Came from around the time of Newton. It was an interesting question. So what the tractrix is. Tractrix is a curve that results when we have we're going to set this up. So here is a coordinate system. It's going to be y and x. And we have a point here on the x-axis. And the point, we're going to say the coordinates of this point are A0. And the origin is here. And we're going to start pulling this point with a rigid connector, which starts at the origin. And whatever the force is that's pulling point A, this point that's over here at A0, is going to move directly up the y-axis. So we're connected to this point with a rigid connection, and we're pulling directly up the y-axis. And we want to know the equation of this curve that this point follows as whatever is pulling it moves directly up the y-axis. So we want an equation for this curve. So we're saying this is some function y equals f of x. And we want to write an equation for that function. So here's whatever the thing is that is pulling. So this would be an example of this. I talked about it briefly in class. If we had a tractor trailer, a semi, and it's at an intersection, and the tractor pulls in the direction perpendicular to where the trailer is, this curve would be the path that the back tires of the trailer follow. The example that they have in the book is we have a boat that's out in the water, and we're pulling it to the dock, which is along the y-axis by walking directly along the dock. So the dock would be here. We're pulling the boat with a rope, and so the boat would follow this curved path. So here is, for a particular point, xy, my connector, do my connector in blue here. So that's my rigid connector. and this is pulling directly up the y-axis. So that's my setup. I'm going to draw a little triangle here. This distance is x. Well, we started out, I know it didn't draw it that way, but I started out at a0. So the length of my connector is going to be a. So initially my connector is here, and I pull here, so the length of my connector is a. And the length of this side of the triangle here is square root of a squared minus x squared. So at any moment, the point is moving only, the point xy is moving only in the direction of the connector. So that's the only force that's being applied to this point, is what travels through the connector. There's no other force. So the point is moving only in the direction of the connector. And this point P, we'll call this point P. P moves directly along the y-axis. So P moves along the y-axis. So at any point, in time, this point is moving only in the direction of the connector. So the connector will be in the direction of the tangent to the curve. The motion at any point is tangent to the curve. So this connector is going to be tangent to our curve at any time, because that's the motion of direction. So remember, that's thinking back to when you talked about vectors in the past, that the velocity vector is tangent to the path of whatever the object is. So the tangent is given by the derivative of that point. The derivative gives us the slope of the tangent, and the slope of the tangent is also this side of the triangle. At this point, the slope of the tangent is the same as the side of the triangle, and the derivative at that point gives us the slope of the tangent as well. So the slope that describes this side of the connector is, and we're going to say negative square root of a squared minus x squared. Based on our diagram, the slope is, we're going to say the slope is negative, divided by x. So at that point, point xy, the derivative gives us the slope. So we're going to say dy dx equals negative square root of a squared minus x squared over x. Well, this is a separable differential equation. We can get the x's on one side and the y's on the other side. So we can rewrite this as dy equals minus square root of a squared minus x squared over x dx. And then I can integrate both sides to solve for y. And then I'll have an equation for my curve. So when I integrate both sides, I get y equals the integral of negative square root of a squared minus x squared over x dx. When I evaluate this integral, this one is not one of our basic formulas. We could look it up. We could look it up in a table. We could evaluate a calculator. Wolfram alpha something would tell us that this equals a times the inverse hyperbolic secant of x over a minus the square root of a squared minus x squared plus c. So this path is described by an inverse hyperbolic trig function. It's a path called the tractrix. It's a or a pursuit curve. Sometimes you'll hear the curve called the pursuit curve. There are lots of pursuit curves, but this one is a pretty famous one, and so a lot of times you hear it called the pursuit curve. We can get this result from trig substitution also. So if I went through and did my trig substitution, I would get this same result. So the trig substitution is very similar to what we did last time. So let me see if I can go through that very quickly. So we have y equals, and I'm going to put the minus sign out front, minus integral square root of a squared minus x squared over x dx. Draw my triangle. Always draw a triangle for trig sub. This side is a, this side is square root of a squared minus x squared, and this side is going to be x. So write my quantities that I need. Tangent theta, square root of a squared minus x squared over x. Cosine theta equals x over a. So x equals a cosine theta. Trying to get my dx here. So dx equals minus a sine theta d theta. Now I can substitute in. So we have minus the integral of minus a sine theta tangent theta d theta. Have to do some work here. This is a, I'm pulling the a out front, a integral of sine squared theta over cosine theta d theta. And I'm going to write my integral just in terms of cosines. So this is a integral 1 minus cosine squared theta over cosine theta d theta. So we get a integral 1 over cosine theta minus cosine theta d theta. Using our nice trigonometric methods for evaluating integrals here. So finally we get a integral of secant theta minus cosine theta d theta, which is a times the natural log of secant theta plus tangent theta, very similar to the last one we did, minus sine theta plus our constant. And when we back substitute our quantities back into our expression here, we get y equals a times the natural log, the absolute value of a over x plus the square root of a squared a squared minus x squared over x minus square root of a squared minus x squared over a I'm going to move this c, so this goes here, plus c, which I can multiply this term by the a. We're not taking the natural log of this term, we're only taking the natural log of this absolute value here. So finally, this simplifies to y equals a times inverse hyperbolic secant of a over x minus the square root of a squared minus x plus a c. So this one took a little more work using trig substitution, recognizing this quantity as inverse hyperbolic secant of x over a from our definition, and we get the equation of a tractrix, or a pursuit curve.